Hey everyone, we're looking at section 7.3 today. Here, this is the last of our conic sections that we are going to talk about, and we're talking about the hyperbola. So as you can see from this image over here, your hyperbola will have two branches, and each of those branches will have its own focus. Now, even the hyperbola has a very interesting reflecting property. So the idea is, if you take a ray of light or sound for that matter and aim it at one of the focus points, it will basically be reflected off that hyperbolic surface, and it will be directed towards the other focus. So you can see, think about these arrows coming in as a light ray, and basically we're trying to focus, send it towards this focus on the right. Like I said, it's going to bounce off this hyperbolic surface, and it's going to start aiming towards the other focus over here. So we use this we use this reflective property in telescopes. So basically what we say is, within the telescope you will have a small hyperbolic mirror, and it will be this mirror right over here on the right hand side, and it's going to have the same focus as the large parabolic mirror. So you will see this one here is our large parabolic mirror. So for this parabolic mirror, this focus on the right is going to be the focus, which is also going to be the same focus for this hyperbolic mirror over here. So that's how the parabola and the hyperbola are being placed, by using that same focus. And basically the idea is, the light that is coming from a distant planet, so that would be this light that's coming, it's going to bounce off the parabolic mirror, and of course it's going to start going towards this focus over here. So your light from the distant planet is coming in, it's going to bounce off this parabolic surface here, and it's going to go towards its focus. But since we're blocking that with the hyperbolic mirror, it's going to bounce off this hyperbolic mirror right over here and get sent towards the other focus over here. And this is where our viewing lens is going to be, and you can see this is where the person will be looking at the planet. So where this focus is on the left hand side, that's basically where we see what that planet or star, or whatever you are looking at, you will be able to view that. So that's kind of how the technology with telescopes works. So if you remember, in section 7.1 I had talked about how we looked at that example for the telescope. We talked about the Hubble Space Telescope. So you can basically think of any telescope that we have, even if you have like one in your backyard, if you want to look at the skies, they're going to have that same reflective property in them. Okay, so let's see the definition for the hyperbola. So we're saying a hyperbola is a set of points in a plane such that the difference between the distances from the two fixed points is going to be constant. And your two fixed points, of course, we're talking about the foci over here. Okay, so basically these branches that we have in the graph of our hyperbola, they may look like parabolas, but by the geometric definition they are not parabolas. Okay, so don't think of them as parabolas, they're just the branches that form the shape of our hyperbola. Okay, so we're saying a hyperbola with foci on the x-axis is said to open left and right. So of course you will see, when our hyperbola opens left and right, you are going to have x-intercepts, and those x-intercepts are going to be at the point negative a0 and positive a0. Our foci, of course, are going to be at c0 and negative c0. And this one, in this case, in this image, we would say is centered at the origin 0, 0. So this would be our center. Okay, so our foci, our x-intercepts, or you can call them as vertices also, both your a and c values are going to be positive, and the line segment, which goes from negative a0 to a0, that's the one right here in between these two branches, is what we call as the transverse axis. And basically halfway between your foci is where you will find the center, which, like I said, is going to be at the origin 0, 0. So when you have a hyperbola which is centered at 0, 0 and it opens left and right. Your foci is going to be on the x-axis also at c0 and negative c0. You will have x-intercepts because your branches will cross the x-axis at a0 and negative a0. And the equation of our hyperbola is going to be x squared over a squared minus y squared over b squared equals 1. And the relationship between our a, b, and c variables is going to be b squared equals c squared minus a squared. Okay? And they're basically telling us the difference of the distances from any point on the ellipse to the two foci is 2a. Actually, I think that should say hyperbola instead of ellipse. The difference of the distances from any point on the hyperbola here to the two foci is 2a. Okay, so again, this is a hyperbola centered at 0, 0, opening left and right, and your equation is going to be x squared over a squared minus y squared over b squared equals 1. Now, if your foci are going to be on the y-axis, then that means your hyperbola is opening up and down. So this is the equation for a hyperbola centered again at 0, 0 and opening up and down. So since our foci are going to be on the y-axis, your ordered pair for the foci will be 0, c and 0, negative c. And this time, instead of x-intercepts, of course, we will have y-intercepts. And those y-intercepts will be at the point 0a and 0, negative a. And this equation is going to end up being y squared over a squared minus x squared over b squared equals 1. And again, the relationship between a, b, and c is b squared equals c squared minus a squared. Or if it helps, you can think of this, if you just move that a squared to the other side, you can think of this relationship as being a squared plus b squared equals c squared, kind of like our Pythagorean theorem formula. So if it helps you remember better this way, you can rewrite this into a squared plus b squared equals c squared. And again, the difference of the distances from any point on the hyperbola to the two foci is going to be 2a. So instead of ellipse, that should say hyperbola. So the big difference you should notice here is when our hyperbola is opening left and right, your x squared is going to be the first variable in the equation. When the hyperbola opens up and down, y squared is going to be the first variable in your equation. So that's how you know if your hyperbola is going to be opening left or right, or if it's going to be opening up or down. Okay, so just to identify the difference between equations for an ellipse and equations for a hyperbola, first thing, with ellipses, you are actually going to have a plus sign in the middle instead of a minus sign that you do here. And then remember, with ellipses, we put the larger denominator under the variable where your major axis is going to be. So in an ellipse, if the larger denominator is under x, that means you have a horizontal major axis. If your larger denominator is under y, then you have a vertical major axis. Now, that's not the case with hyperbolas. With hyperbolas, as I was mentioning before, if your x squared variable is the first one in your equation, then your hyperbola is opening left and right. If y squared is the first variable in your equation, then your hyperbola is opening up and down. So it really doesn't matter where the larger denominator is. Okay, and then whichever denominator is underneath the x and the y variables, those will be your x and y intercepts respectively based on that variable. Okay, alrighty, let's talk about the graphing for a hyperbola. So the graphing of a hyperbola is a lot different than anything we have done so far with parabolas, ellipses, and circles. So the first thing we actually need for graphing our hyperbolas are these equations for the oblique asymptotes. So when your hyperbola is opening left and right, the equations for your asymptotes are going to be y equals b over a x and y equals negative b over ax, which forms these diagonal lines or these oblique asymptotes, as you can see here. So here we have y equals b over ax, and here we have y equals negative b over ax. Okay, and of course these values of a and b are coming from your equation itself. And then we take these four ordered pairs, AB, A negative B, negative AB, and negative A and negative B. These will become the four corners, or basically the four vertices of what we call as our fundamental rectangle. So basically what you can actually do is start by first drawing this fundamental rectangle, and you will see all of these lines are dotted lines or dashed lines because these lines don't actually exist. These are just guidelines to help us come up with the branches of our hyperbola. So all of these are going to be dotted lines. The only solid lines are going to be the ones for your branches. So start by drawing the four vertices for your fundamental rectangle, and then basically if you extend those diagonals for the rectangle, they will become your asymptotes. So that will give you the b over ax and negative b over ax. And then they are talking about the line segment that has the endpoints of 0, b, and 0, negative b. So they're actually talking about this line segment here is what we call as the conjugate axis. So remember, the smaller one is the conjugate axis and the longer one is the transverse axis. Okay? Alrighty, so now let's go ahead and take a look at our example here. And again, this is the relationship between your a, b, and c variables. So c squared equals a squared plus b squared. And they're saying since the distance c from the center to the focus is going to be equal to the distance from the center to the point AB. So the distance from the center to the focus, so they're talking about this distance here is going to be the same one from your center to the point AB. So they're talking about these two distances here. So this distance and this distance is going to be the same. Okay? Alrighty, and this one here is actually just showing you an illustration so that you can see the relationship between your A, B, and C values. So that's where our idea of A square plus B square equals C square is coming from, just using that Pythagorean theorem. Okay, so just the steps involved in graphing our hyperbola, and this is for our hyperbola that is opening left and right. Okay. So of course you can see both our A and B values are going to be positive. The coordinates A and negative A will give us our x-intercept, so A0, negative A0. We draw our rectangle, they are saying through the points positive and negative A0 and through the points 0 and positive and negative AB. But basically remember, you can use your vertices as AB, A negative B, negative A positive B, and then negative A negative B. Extend the diagonals of your rectangle to come up with the asymptotes, which would be our oblique asymptotes, and then of course we would draw our hyperbola opening left and right, which will pass through the x-intercepts and of course approach the hyperbola. So let's take a look at our first example here. They're asking us to find the foci, find the equations of the asymptotes, and then sketch the graph of our hyperbola. Okay? Alrighty. So as I was saying earlier, the number that you have underneath the x variable will represent the x-intercepts, and the variable you have underneath the y-axis will represent the y-intercepts. Okay? So in this case, our a square value, there we go, is going to be 4, which means a is going to be 2, right? And b square is going to be 9, and of course that means b is going to be the value of 3. So if we talk about the vertices of our fundamental rectangle, because that's the first thing we need to grab, so those vertices are going to be AB, A negative B, negative AB, and negative A, negative B, right? We just go with different versions of positive and negative for each of these numbers. So to be 2 comma 3 to negative 3, negative 2 positive 3, and then negative 2 negative 3. So these guys are going to be, let's see, positive 2 positive 3, positive 2 negative 3, and then negative 2 positive 3, negative 2 negative 3. So these guys here will form our fundamental rectangle. Okay, and then if you extend out these diagonals, then we have our oblique asymptotes. Okay, and same thing for the other diagonal. So let's see, and I'm doing this freehand, but I definitely recommend that you guys use a ruler when you are doing this, so you get nice and good straight lines and not just something off here, which this line was not correct. So something like this. Okay, alrighty, so let's see, we have our fundamental rectangle. Now remember, the oblique asymptotes, those equations are going to be y equals b over ax and y equals negative b over ax. So that means we have y equals 3/2 x and y equals negative 3/2 x. So that's going to be our oblique asymptotes. Okay, so they did ask us to find the equations of the oblique asymptotes. We do. Now all we have to do is sketch our graph and determine where our foci are going to be. So let's do the graph part first. So since you can see our x squared was the first variable, so this tells us that we are in fact looking at a left and right hyperbola. So this hyperbola will open left and right. And then of course our x-intercepts are going to be at a0, a0 and negative a0. So those are going to be positive 2, 0 and negative 2, 0. So right over here we have our x-intercepts, and then when you're drawing the branches of your hyperbola, basically you will go along this fundamental rectangle till you get to that oblique asymptote. And then remember, with the asymptotes, your graph will get closer to that asymptote, but it will never touch that asymptote and it will never cross it. So that's what your branches are going to do. They're going to get close to these asymptotes, but obviously they're not touching or crossing them. And then make sure you are actually crossing at the x-intercept also, so you should be crossing at these points over here. And this is basically what our sorry about that, this is what our graph ends up looking like. So this is our hyperbola opening left and right, centered at 0, 0. Now let's talk about the foci for this. So remember, the relationship between a, b, and c is a square plus b square equals c square. Our a square value, and you can get that from your denominators, our a square is 4, b square is 9. 9 plus 4 will of course give us 13, and then to find the value of c, we will take a square root on both sides, and again, right now we're just looking at the positive roots only. So that will end up giving us c equals square root of 13. Now since this is a hyperbola opening left and right, our foci are going to be at square root of 13 0, and negative square root of 13, 0. So these are the foci. Now if we just wanted to graph these on our coordinate plane, then let's just see quickly approximately what is square root of 13. And square root of 13 is approximately 3.6. So if we try to graph these on our hyperbola, 3.6 will be somewhere over here, and then negative 3.6. So this is square root of 13, 0, and this is negative square root of 13, 0 for our foci. Okay, so as I was showing you here, the main thing is getting that fundamental rectangle, extending the diagonals to form your oblique asymptotes, get the equations for your oblique asymptotes, and then figure out what your foci coordinates are going to be, and then just plot them on your graph over here. Okay, so there we go. This was our example 1. Now, instead of opening left and right, what if your hyperbolas are opening up and down? So in that case, the equations of your oblique asymptotes will change. They will now become y equals a over bx and y equals negative a over bx. And then of course the equation of our graph is going to be y square over a square minus x square over b square equals 1. So you will see y square will now become the first variable in this case. Now the 4 vertices of our fundamental rectangle are also going to change. So they will become negative BA, positive BA, negative B, negative A, and positive B, negative A. Instead of having x-intercepts, we will now have y-intercepts at 0, A, and 0, negative A. Okay, so of course start by first locating your y-intercepts. Again, your A and B values will be positive. This is the equation of our hyperbola that opens up and down. Okay, draw your rectangle through these points, but basically you are looking at BA, B, negative A, negative B, positive A, and negative B, negative A. These will be the 4 vertices for our fundamental rectangle. Draw your diagonals into the asymptotes, and then of course draw your hyperbola opening up and down through those y-intercepts approaching the asymptote. So let's go ahead and take a look at this example here. Alrighty, so again the value underneath y square will give you the y-intercepts. The value underneath the x square will give you your x-intercepts, but in this case my first denominator is still going to be a square, which is 4, which means a equals 2. My b square is the second denominator, which will be 25, which means b equals 5. And from the a value, we are going to get our y-intercepts. So the y-intercepts will be at 0a and 0, negative a. So they are going to be 0, 2 and 0, negative 2. We can now get the 4 vertices of our fundamental rectangle. And remember, these ordered pairs are going to be BA, B, negative A, negative BA, and then negative B, negative A. So let's see, this will be 5 and 2, 5 and negative 2, negative 5, 2, and negative 5, negative 2. Okay, so let's go ahead and plot these on our graph. So we've got positive 5 and positive 2, positive 5 and negative 2, negative 5, positive 2, negative 5, negative 2. So this here will form our fundamental rectangle. And then of course we go ahead and extend our diagonals. Okay, so this will be going out here. So the other one going out this way. Okay, so these would be our diagonals over here. Now let's talk about the oblique asymptotes. So remember, this time your equation is going to be y equals a over bx and y equals negative a over bx, okay? So that would be y equals 2 over 5x and y equals negative 2 over 5x. And you can use these equations also to help you draw the oblique asymptotes if you think that would be easier. Okay, so we have our oblique asymptotes. Now let's go ahead and do the graph for our hyperbola here. So remember, your y-intercepts are at 0, 2 and 0, negative 2, and this is a hyperbola that opens up and down. And remember, we know that because y square is our first variable here. So this one will be going, again, passing through that y-intercept, and it's going to be going towards your oblique asymptotes here, and then it's going to be going towards your oblique asymptote over here. Okay, and then the second branch down here, maybe something like this. And there you go. This is our hyperbola opening up and down. Now the very last thing we have to do is our foci. So let's take a look at that. Again, it's a square plus b square equals c square. Our a square value is 4, b square is 25, which will of course add up to give us 29. And then we do square root on both sides. And again, remember guys, we're only looking at the positive root here. So you end up getting c equals square root of 29. Now this is a hyperbola that opens up and down, which means our foci are going to be on the y-axis. So these ordered pairs would be 0, square root of 29, and 0, negative square root of 29. So here we have our foci. So again, foci, oblique asymptotes, and the graph is what they were asking. Now let's see approximately where is square root of 29 going to fall on our graph. So this comes out to be approximately 5.4. So if we try to graph this, 5.4, so let's see, these guys are 2, 3, 4, 5, 5.4, maybe about there, 2, 3, 4, 5, so 5.4 over here. Okay, so this will be 0, square root of 29, and this will be 0, negative square root of 29. Okay, so again, same process. Find the fundamental rectangle first, extend your diagonals to form the oblique asymptotes, get your equation for the oblique asymptotes, and then find your foci. Alrighty, now what happens if our hyperbolas are not centered at 0, 0 and they are centered at a point hk? So just like you saw with the ellipses, how your when the center moves, all the points have to move. You will see something similar over here with these examples also. So you will see when your center is at hk, your equations will change, and you will have x minus h quantity squared over a square minus y minus k quantity squared over b square equals 1. But again, if the x variable is the first one, then your hyperbola is opening left and right. And then if you have y minus k quantity squared over a square minus x minus h quantity squared over b square equals 1, and the y variable is the first one, that means your hyperbola is opening up and down. Okay, So in this case, we are basically saying that you will have, when the x is the first variable, you have a horizontal transverse axis. When you have y squared as your first variable, then you have a vertical transverse axis. And then of course your foci and vertices will fall on the transverse axis, because at this point you will not necessarily be on the x or the y axis because your center is at hk. These lines will have moved, and they are saying the distance from the center to the vertices is a, the distance from the center to foci is c, where your relationship is going to be c squared equals a squared plus b squared, where both a and b are going to be positive numbers. So same thing, they're asking us to determine the foci, come up with the equations of the asymptotes, and then sketch the graph for these hyperbolas. So let's go ahead and take a look at this example 3 over here. Okay, so the first thing we want to do is go ahead and find our center. So again, you can see we have x plus 1, so that tells us our x coordinate is going to be -1, and we have y minus 2, so our y coordinate is going to be positive 2. So when we're talking about the center of our hyperbola here, we're talking about -1 and positive 2. So you will see, instead of our center being at 0, 0, we are now moving 1 unit to the left and 2 units up. So the graph moves 1 unit left and 2 units upward, right? And this is something we're going to have to do with all of our points. So let's start by first finding our vertices for the fundamental rectangle, and then we'll have to make this change happen, right? So let's look at our a square value is 4, which means a is going to be 2. Our b square value is 9, which means b is going to be 3. Now, your x is still the first variable you see in your equation. So this still tells us that our graph will open left and right. So normally, you would have had your x-intercepts for the original function at a0 and -a0, which will end up becoming 2, 0 and -2, 0. But since our graph is moving 1 unit to the left and 2 units upward, that means we will be subtracting 1 from the x value, and we will be adding 2 to the y value. So these new points will end up becoming, let's see, 2 minus 1 is 1, 0 plus 2 is 2, and then -2 minus 1 will become -3, 0 plus 2 is 2. So these will, instead of calling them our x-intercepts, how about we call these guys as our vertices for our transverse axis, right? So that will be, let's see, +1, +2, and then -3, +2. So these are going to be your vertices, and this is where your graph will be crossing the transverse axis at, okay? Alright, so now we need to do our fundamental rectangle. And so since this is a hyperbola opening left and right, our fundamental rectangle vertices are going to be AB, A, -B, -AB, and -B, which comes out to be 2, 3, 2, -3, -2, 3, and -2, -3. But these were for the original hyperbola if you were centered at 0, 0. So remember, we are moving 1 unit left, so subtract 1 from each of the x-axis, and we are moving 2 units up, which means add 2 to each of the y-axis. So our vertices for the fundamental rectangle are now going to be, let's see, 2 minus 1 is 1, 3 plus 2 is 5, 2 minus 1 of course is 1, negative 3 plus 2 is negative 1, negative 2 minus 1 is negative 3, 3 plus 2 is 5, and negative 2 minus 1 is negative 3, and negative 3 plus 1 is negative 1. So we are looking at our vertices for the fundamental rectangle. These ones are the new vertices. So they will be at 1 and 5. So let's see, 1, 1, 2, 3, 4, 5. And then what did we have? Negative 3 and 5. And then we had positive 1, negative 1. And we've got negative 3, negative 1, okay? So this here will form our fundamental rectangle. Let me see. And then when you extend out the diagonal, and we're going to use our center to help us out a bit. Okay, let's see. As straight as you possibly can. Now, like I said, again, if you have a ruler, these lines will come out to be a lot better than trying to do them freehand, like I am, and it doesn't look like I'm doing a very good job, but let's go ahead and do it. Something like that. Alrighty, and then when we are drawing our, well, let's do the equation for our oblique asymptotes. Okay, so again, since this is a hyperbola that opens left and right, typically our equations have been b over ax and y equals negative b over ax. But in this case, of course, that is going to change because we still have our b value as 3 and a as 2. So this would be 3/2 x and y equals negative 3/2 x. But remember, this was when you had the center at 0, 0. But now that our center is moving from 0, 0 to negative 1, positive 2, we are actually going to have to use the point slope form of the equation of a line to come up with our new equations. So in this case, we would actually say the slope of our line are still going to be 3/2, but now we will be passing through the point negative 1, 2, and you can see that, right? Our oblique asymptotes are passing through the center of negative 1, 2, so we need to take that into account. So remember, your point slope form of the equation is y minus y1 equals m times x minus x1. So we'll need to use that for both our positive and negative slopes. So this should be one's positive and one's negative. So let's do, this will be our point x1, y1. Let's start with the positive slope first. So you would have y minus 2 equals positive 3/2 x minus negative 1. And of course that ends up becoming x plus 1 inside the parentheses. Then of course distribute that 3/2 inside the parentheses. You get y minus 2 equals 3/2 x plus 3/2 times 1 of course is 3/2. Add that to the other side and get y by itself, and this is how you come up with the equations of your asymptote. So you will end up with y equals 3/2 x, and then you are adding 3/2 plus 2. How about we write it here? 3/2 plus 2. You have to find a common denominator, so multiply by 2. You get 3 plus 4, which will give you 7, and you end up getting 3/2 x plus 7/2. This is going to be one of our equations for the oblique asymptote, and then for the second one, we will need to use a slope of negative 3/2. Okay, so now let's do this again. Y minus 2, but now we have a slope of negative 3/2, x minus negative 1. So we get y minus 2 equals negative 3/2. Two negatives will make it a positive, so x plus 1 over here. Just like we did before, distribute that negative 3/2 inside the parentheses, and we end up getting negative 3/2 x minus 3/2, and then again add this 2, move it to the right hand side, get y by itself, and you have again common denominator, multiply by 2, and this time you're looking at y equals negative 3/2 x, and then minus 3 plus 4 will actually give us plus 1, and that will end up giving us plus 1/2 over here, and this will be our second equation for our vertical asymptote. So the positive slope is going to be this line here, the asymptote with the positive slope, and then the negative slope is of course our second line over here. So this is how you come up with your equations for the oblique asymptotes. Okay, so let's go ahead and do our graph, and then we'll come back and look at the foci for these for this example over here. So again, your hyperbola is opening left and right, passing through these points that I already have here. So again, you will be getting closer to that asymptote. This one here will be getting closer to this asymptote, and then the other branch. Then you're kind of going like this, and then coming down this way. And that's what the graph will look like when the center is not at 0, 0, because your center here is at negative 1, positive 2. Okay, now let's talk about the foci. Again, our relationship here is going to be between A, B, and C. A square plus B square equals C square. So let's see, our A square is 4, B square is 9, which will add up to 13. Take a square root on both sides, and again we're only keeping the positive root only. So you will end up getting C equals square root of 13. Now this would have been for our original, and since this is again opening left and right, you would have had square root of 13, 0, and negative square root of 13, 0. But again, remember our graph is moving 1 unit to the left, 2 units up. So subtract 1 from the x, add 2 to the y values, and you will end up getting the new foci are going to be negative 1 plus square root of 13, and 0 plus 2 will be 2, negative 1 minus square root of 13, and again positive 2. So these would be the new foci for our graph. And just to see what those approximate values would be, let's go ahead and see what those decimal approximations are. So -1 plus square root of 13 gives you an approximate value of, looks like 2.6, and of course our y coordinate is 2, and -1 minus square root of 13 gives us -4.6, and of course 2 is our y coordinate. So let's see, 2.6 and 2, so that's 1, 2, 2.6 and 2, so this is your -1 plus square root of 13 comma 2 for your first foci, and then -4.6 and 2. So let's see, -4.6, so this is 1, 2, 3, 4, 4.6 would be somewhere over here, and this is going to be the point -1 negative square root of 13 comma 2. Okay, and that's where your foci are going to be. So again, just look through the example of how we came up with our oblique asymptotes, how we do the new focal points, how we came up with the new values for the fundamental rectangle, and basically every point will change here. Okay, so this is number 3. We have one more example, and this is for a hyperbola that opens up and down, and how does that make a difference? So let's go ahead and take a look at this example over here. Alright, so again, we'll start by finding our center. So you can see the x value is x minus 1, which means x itself is positive 1. And the y value is y minus 2, so that means y itself is going to be positive 2. So let's see, positive 1, positive 2. So from 0, 0, our graph is moving 1 unit to the right and 2 unit upward. So we say the graph moves 1 unit right and 2 units upward. Okay, so your a value is going to be a square is 4, which means a value is 2. B square is 9, which means B value is 3. Now the A value, again, since this is y square as our first variable, this actually tells us this is a hyperbola that opens up and down. So that means the A value is actually giving us the y-intercepts. So the y-intercepts would have been 0A and 0, negative A, which means they would have been 0, 2, 0, negative 2. But now that our graph is moving 1 unit right and 2 units upward, we'll need to change those values, and they will become 0 plus 1 is 1, 2 plus 2 is 4, 0 plus 1 is 1, negative 2 plus 2 is 0, and these become the vertices for your transverse axis. So that's going to be positive 1, positive 4, and positive 1 and 0. So these are the points where the branches of our hyperbola will be crossing. Okay? Now we need to come up with our fundamental rectangle. Now, since this is a hyperbola that opens up and down, these will be B and A, B negative A, negative BA, and then negative B, negative A. So B is 3, A is 2, so that would be 3, 2, 3, negative 2, negative 3 and 2, and negative 3, negative 2, right? So those become the vertices for the original hyperbola, which was centered at 0, 0. So in this case, all of our x values are moving 1 unit to the right, and all of our y values are moving 2 units up. So we need to make these changes, and this will give us the new vertices, which will be 3 plus 1 So if it will let me write, there we go, 3 plus 1 is 4, 2 plus 2 is also 4, 3 plus 1 is 4, negative 2 plus 2 is 0, negative 3 plus 1 is negative 2, 2 plus 2 is 4, and then negative 3 plus 1 is negative 2, negative 2 plus 3 of course will give you 1 over here. Okay, not sure what happened. There we go. Negative 2 plus 3 will give you, oh, I don't know why I did plus 3. That should be plus 2. So this will be incorrect. So negative 2 plus 2 will end up giving us 0. Alright, so these would be the new vertices for our fundamental rectangle over here. So let's go ahead and plot these. 4 and 4. So let's see, 1, 2, 3, 4, 1, 2, 3, 4. Right over here. And then let's see, 4 and 0 would be right over here. Negative 2 and 0 and negative 2 and positive 4. So this here will form the fundamental rectangle, right, for the hyperbola. And then we can extend out our diagonals, which will go from here and continue down here. Okay, something like that, and these should be more dotted lines than solid. Okay. Something like that. Let's do the other one. So again, diagonals going out. I think that one didn't come out quite right, so let me try that one more time. Okay. Alrighty, so there we go. We have our oblique asymptotes now. Now let's go ahead and talk about the equations for our oblique asymptotes. Okay, so again, remember, this is a hyperbola that opens up and down, which means your equations would have been a over bx and y equals negative a over bx, which in this case would have been 2 over 3, right? So positive 2 over 3x and negative 2 over 3x. So of course we need to talk about what the equations will be, what the equations will be when we are moving the center from 0, 0 to positive 1, positive 2, right? So again, that means we would use the slope as positive and negative 2/3, and our point would be 1 and 2, which is the center. And of course, remember, you're using your point slope form of the equation of a line to come up with these equations. So let's start with the first one. We'll do y minus 2 equals positive slope 2/3 x minus 1. So we need to start by distributing this x inside. Sorry, the 2/3 inside with the x and the 1. So y minus 2 equals 2/3 x minus 2/3, and again we are adding this 2. Make a common denominator, which will be 3 this time. So you get y equals 2/3 x, and then I have negative 2, and this here will give me positive 6. So negative 2 and positive 6 gives us a positive 4. So we end up getting positive 4/3 as one of our equations for the oblique asymptote. Now let's see what happens when we use the negative slope. So that would be y minus 2 equals negative 2/3 x minus 1. Same thing, distribute that. And oh, just remember, this is our ordered pair x1, y1 that I'm putting in our equation here. And then of course for our slope, so that will give you negative 2/3 x. Negative times negative is positive, so that becomes positive 2/3. Add that to, same thing, find a common denominator, so that will end up giving us y equals negative 2/3 x. And now I am adding positive 2 with 2 times 3 is 6, so positive 2, positive 6 will of course end up giving us positive 8/3, and that will be the second equation for our oblique asymptote. So there you go. For the line with the positive slope, that's going to be y equals 2/3 x plus 4, and the line with the negative slope will be y equals negative 2/3 x plus 8 over 3. Now let's go ahead and graph our hyperbola here. So again, passing through those points and then getting close to the oblique asymptotes. So something like this, and then our second branch. Okay, so this would be something like that. Alrighty, and now let's find our foci. So original relationship, a square plus b square equals c square. A square is 4, b square is 9. Again, that adds up to 13. Take a square root on both sides. We're again only keeping the positive root. And we will end up getting c equals square root of 13. Now these are hyperbolas opening up and down, so your ordered pairs would have been 0 square root of 13 and 0 negative square root of 13 for the original. Since our center is moving 1 unit to the right and 2 units up, your new foci would end up being the point 0 plus 1 is 1, 2 plus square root of 13, and then again 0 plus 1 is 1, and 2 minus square root of 13. These would be your ordered pairs for the new foci. But let's see approximately where are these points going to fall. So we have 2 plus square root of 13. Okay, so 2 plus square root of 13 will end up giving us approximately the ordered pairs 1 comma 5.6 for this first one, and this here should actually be a 1 because 0 plus 1 is 1, and this guy would be 1 comma 2 minus square root of 13 is negative 1.6. So let's go ahead and put these on our graph over here. So positive 1 and 5.6. Let's see, positive 1, 1, 2, 3, 4, 5.6. So somewhere over here, and this would be 1 comma 2 plus square root of 13. And then for the other one, we were at negative 1.6. So that's 1 and negative 1.6 would be somewhere over here, and this would be the ordered pair 1 comma 2 minus square root of 13 for our second foci. And so this is where you would find the foci for this hyperbola. Okay, so we moved our y-intercepts, we moved our vertices for the fundamental rectangle, we got the equation for our oblique asymptotes, and then we found the new foci values. Okay, so we have basically done everything that they had asked us to do here in these two examples. Okay, so the last thing that we want to talk about here is what happens if they give you the asymptotes and the x-intercepts and they ask you to find the equation of your hyperbola. So they are not giving you the equation, They're giving you the asymptotes and they're giving you the x-intercept. So let's see what information we can gather from that. So when they're telling you that you have your x-intercepts, that actually means this is going to be a hyperbola that opens left and right. So just as a rough sketch over here, so let's say this was our grid, and if they are giving you your x-intercepts 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, that means your, and this is just a rough sketch here. Ooh, that's really terrible. Okay, just the branches of our hyperbola are going to be crossing the x-axis, right? So this actually tells us this is a hyperbola that opens left and right, and that's why we know, because we have the x-intercepts, right? So remember your x-intercepts, let me go ahead and write the general form of the equation first before I talk about that. Okay, so this will be the general form of our equation that opens left and right. So remember the x-intercepts, that means are giving you your a value. So this is actually giving you the values of a0 and negative a0. So that tells us if the a value is 6, then that means a square is going to be 36. So we can already get the a value, but now we need to find the b value, right? So that we can get our b square, and that's where these equations of the asymptotes will come into play. So remember, for hyperbolas that are opening left and right, your asymptotes are in the form of b over ax and y equals negative b over ax. So we actually have to use the idea of proportion to help us out. So we are given b over a is going to be 1/2, right? Let me go back up here. So you can see if we have b over ax and this is 1 over 2, then of course b over a has to equal 1 over 2. So that's where I'm getting this idea of b over a equals 1 over 2. Now we know the value of a is 6, which is coming from our intercept. So you can write a as 6, and this will of course equal 1/2. And solving this proportion, you can come up with the value for b, which will be by cross product. So you will end up getting b times 2 is 2b, 6 times 1 is 6, divide both sides by 2, and you end up getting b equals 3. So if b equals 3, that means b square is going to equal 9, right? So if b square equals 9 and a square equals 36, we can put our equation together now, and that equation will come out to be, again in the general form, that's x squared over a square minus y squared over b squared equals 1. So this will now become x squared over a squared is 36, minus y squared over b squared is 9, equals 1. And this is going to be the equation of our hyperbola opening left and right with the asymptotes y equals 1/2 x and y equals negative 1/2 x, and your x-intercepts at 6, 0 and negative 6, 0. So not too bad, you know, once you figure out what information you have available and how you can tie it with the equation of your hyperbola. Now the next one is kind of similar. They're still asking us to find the equation of the hyperbola, but they're giving us the foci and they're giving us the x-intercepts. So again, let's do a quick rough sketch for this. Alright, so let's see, they're telling us the foci is on the x-axis, so 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, negative 5, 0, right? So negative 5, 0 and positive 5, 0. This is the foci, which is on the x-axis. And then you have x-intercepts at 3, 0 and negative 3, 0. So again, if your x-intercepts are at 3, 0 and at negative 3, 0, again, that's telling you that this is a hyperbola that is opening. Oh, if it will let me do my graph. There we go, opening left and right. And this is again just a rough sketch over here. So again, opens left and right. So that means the general form of our equation again is going to be x squared over a squared minus y squared over b squared equals 1. So your x-intercepts will give you the a0 and negative a0 coordinates. Remember, your foci will give you the c0 and the negative c0 coordinates. So we know a is equal to 3, which means a squared is going to equal 9. Now to find b squared, we are going to have to use the relationship between a, b, and c. So let's see, we know c is equal to 5, which means c squared is equal to 25. So we need to find b. And to find b, again, we're going to use the relationship a squared plus b squared equals c squared. A squared is 9. C squared is 25, and we're trying to find b squared. So start by subtracting 9. And of course, you end up getting b squared equals 25 minus 9 will give us 16. So now that we have our a squared and b squared, we can find out our equation. And of course, if b squared is 16, then that means the b value is going to be 4. All right, so let's go ahead and put our equation together. And we have x squared over a squared, where a is 9, minus y squared over b squared, where b squared is 16, equals 1. And this is going to be the equation of our hyperbola here. So just two different types of examples to show you how you can come up with the equation of your hyperbola based on what information you are given. Okay, and I believe this is our last example. Yeah, so there you go. So again, guys, look through the notes, look through your video, let me know if you have any questions. So this would be the end of our chapter 7 and the end of our conic section. So again, we have looked at parabolas, ellipses, circles, and hyperbolas. Okay, so again, if you have any questions, let me know. I will see you in class next time. Be careful, stay safe, and have a great day, guys. Bye-bye.